good time chatting and catching up with folks, but we're going to get started on the session. Welcome back. My name's Dale Peabody. I'm the advisory board chair for the TIDC work. I worked at the Maine Department of Transportation for 40 years, and I retired a couple of years ago after serving in several different positions. What we wanted to do with this session is highlight some work that the universities, the partner universities within the TIDC had completed, and the hope was also to get at, are those results being implemented, what the path to implementation is for these results. So we have 4 excellent speakers, and we'll get right into that. The first presentation is on real-time wireless joint monitoring system for highway bridge resilience. It's given by Dr. Shinae Jang, professor and resident of civil and environmental engineering at the University of Connecticut. She received her BS and MS from the Korea Advanced Institute of Science and Technology and her PhD from the University of Illinois at Urbana-Champaign in civil engineering. Dr. Jang's research interests include wireless smart structures, structural health monitoring, non-destructive evaluation for infrastructure resilience, and engineering education. She's a licensed professional engineer in Connecticut. Welcome, Shinae.
Thank you, Dale. Good afternoon, everyone. Yeah, thank you for being here, not sleeping. It's last session, and then I'm very honored to be here. It is my first TIDC conference presenting my research. I'm Professor Shinae Jang from UConn, and then today's topic is real-time wireless joint monitoring system for highway bridge resilience, and that is outcome from 2 of TIDC research projects. And then I like to proudly introduce my PhD student, Prakash Bandari there. He did most of the work. And then my 2 co-PIs, Professor Song Han from Computer Science and Professor Ramesh Malla from Civil Engineering. Okay, so today, so I expected small breakout sessions, so prepared conference style presentation. So this is my agenda, but I hope to be quick and then to the point. So I'll introduce my project and then talk about joint monitoring practice in New England, and the developed wireless system monitoring system, and then bridge deployment, because that's important, and some preliminary results and conclusion with acknowledgement. So this is the TIDC research project we got. So we started in 2021. So the topic is wireless joint monitoring system, WJMS, for safety of highway bridges. And then this is first project to develop the system, monitoring system, and then a few validation. And then the second project is extension of the first project to validate for larger movement joint and then more deployment. So I'm glad to present some of the deployment work in this last session. So let's see. 1 page of introduction. So joint impacted heavily by climate change. So global warming can contribute to failure of 1 in 4 steel bridges, right? And then most common problem under climate change could be expansion joint because of extreme temperature fluctuation and the movement, and those failures, the failures in expansion joint could lead very significant failure in the bridge. So that's why we look into joint expansion joint systems in the bridge. Also, most of you are focusing on the superstructure and the deck and new construction, but we still have a lot of existing structure, and then failure in the support expansion joint is very important. So that's why we are looking into. And then when we look into some literature, expansion joint monitoring was still limited. So that's the motivation of this research topic. And then we started our project with a survey with 6 New England DOTs, so Connecticut, Maine, Massachusetts, New Hampshire, Rhode Island, and Vermont. And then luckily we got all responses from all 6 DOTs. Thank you so much if you are one of them. And I'll talk about my question, and then this slide will show the answer. So we asked the most common bridge type in New England. So this girder bridge, right? And then the most common expansion joint type, so that's asphaltic plug joint is the most common. And then next, how often do you inspect the joint? It's 2 years mandated by Federal Highway Administration. And then factors impacting joint health. So there are multiple regions. So debris, field construction, variability, and then structural movement due to climate changes as well. And then benefits of joint, what do you think about benefits of joint monitoring systems? And these are what the DOT experts responded. So impact of the loads, further understanding of impact of the load, and then better maintenance planning, and then design and materials, and also understanding temperature and displacement correlation on the climate change. So that's what they suggested. However, because of limited resources to construct the new bridges and also other things, expansion joint were not monitored with professional monitoring systems, but this is understandable. So with this survey result, we started thinking about design requirement. Because joint was not monitored because of limited resource, we cannot think of very expensive or high cost monitoring system. So our first constraint is low cost system, but low cost doesn't mean low quality, right? So we thought about this requirement. So real-time wireless communication to reduce costs, but to use high, so state-of-the-art communication technology, and then complete software, hardware, field system package so that the users can easily use it. And then long-term permanent system with stable power and possibly using renewable energy, and then easy and non-invasive installation retrieval for our precious infrastructure. So those are 5 requirements we thought about for our project with low cost. So it looks like impossible, but it was what we identified. And then we started collaborating with our computer science department Professor Song Han, and his lab has already developed multiple real-time communication platform, including WPC to RT Wi-Fi. And these are available in computer science, but not used in civil engineering or bridge monitoring. And we could choose one of them based on their energy efficiency and or performance. So this way is energy efficiency, so low cost this way. And then this way is high efficiency. But for expansion joint monitoring, we need to have very high fidelity displacement measurement with temperature and humidity. So we cannot sacrifice performance. So we chose a medium 6-inch network. Okay, so that's real-time communication network. And then we developed, so from the first project, we developed a system here using the remote node at the expansion joint with ultrasonic displacement sensor with temperature and humidity monitoring because it's environmentally factored. With communication board, and then gateway node for the processing, and then the brain of the system, and then it is uploading all the data to the cloud server from Amazon Web Base, so cloud computing. So these two are the major part. And to validate our system's fidelity, we use the reference sensor using LVDT displacement, the traditional system, LVDT transducer, and then commercial GoV wireless temperature. So this LVDT and then commercial temperature humidity sensor with this wireless sensor board, ultrasonic and temperature humidity. So these are sensors, and then these are the remote node, and then this is the gateway node, and then these two are communicating with a 6-inch network. And then the measured data was viewed in the graphical user face from the web. So when you click this link or access to the cloud server, and then you can see this data visually, graphically, using the sensor protocol topology and performance as well. So that's the developed system. And then we deploy this developed system into 3 bridges. First one is bridge 1 in Coventry, closest to Yukon. So maybe 10-minute drive from Yukon. And then it is about 75 feet simply supported continuous stack beam. And then there's no skew. So it's simplest bridge. So simple short bridge with the most common joint, asphaltic plug joint. So that's the first bridge to validate our system. And then from here, we validate the system is working fine, reasonably. So I'll show you the data in the next slide. But based on that one, we expanded and then deployed our system into these two other bridges. So the second bridge is in Windham. It's about 20-minute drives from Yukon, a little bit farther, and then twice more length, so 250 feet. And then more noticeable difference is the skew angle, so 45-degree angle. And then the expansion joint strip seal joint, and it is kind of small to medium movement joint. And from this skew angle, we successfully also measure the displacement data as well. And then move on to the Founders Bridge. So that's the still data collection is still going on, and it is very long bridge, a major bridge in Hartford, the capital of Connecticut. And although there's no skew, but we are using, the bridge is using modular expansion joints as a large movement joint. So these three bridges are actually covering from the small movement joint to the large movement joint to validate the effectiveness of the developed system. So I show you the data. So it's preliminary data from the bridge one. So for the first project. So you see the temperature plot from the blue is remote nodes. So blue is our target, and then red is reference. So traditional, a traditional sensor. And then there's slight changes and then delays between these two, but this is reasonable match in my perspective. And then the humidity. The same thing. Blue is remote node, and then red is reference, the commercial sensor. And then the trend is very similar, although there is a slight delays. And then the third one is displacement over time. And then blue, again, blue is wireless, and then red is reference sensor. And then we see very close matching together. And then why is it so flat? Because their temperature doesn't change much. So it's about 2-3 degrees in Fahrenheit changes this time. So the displacement of the expansion joint was very small. And then it's not noticeable from the sensor. So from here, we got some confidence and then move on to the second bridge. So it's 250 feet bridge, right? And then here we attach it to sensors, displacement sensor at the middle of the girder and then bottom of the girder. And then you see the solid line is in the middle, and then the broken line is bottom of the flange. And then although there's some change, so there's this changes, this constant changes, but the trend is the same. And then red line is the temperature. So when you compare with displacement trend and then temperature trend, and then it is following correctly. So and with about 10 degrees in Celsius, sorry about the units, Celsius changes, we see about 6 millimeters, so it's about less than 1/3 inches of displacement in the expansion joint, and that is acceptable for the medium movement joint. So we confirm that the performance of the bridge is correctly done. And then the last bridge is the Founders Bridge, the huge bridge in Hartford region. So here the blue line is displacement over 2 days, and then the red line is the temperature of the girder, and it is following the same trend. So so these are only representative data, I like to say that, and then the data collection is still going on from this Founders Bridge, and then we are doing the data analysis, and then other analysis here. So the performance of the developed wireless joint mode system, we think it's reasonable, and we will continue doing data analysis. Okay, and then here, is time good? Is time good? Yeah. So here I like to show you some cost comparison with the wired system as of 2022. So I include only sensors and then communication. And the second and third columns are the costs from the wired system. And then the fourth and the fifth line is cost from the wireless system, including only sensors and communication portion. And then you can see the differences. Wired 3,000, more than 3,000, and the wireless 150. And then it is about less than 5% of cost. So I cannot say our data is perfect, but with less than 5% of cost of the wired system, I think the performance is reasonable. And then because we have more existing bridges and then old bridges to monitor, and the understanding of displacement and the expansion joint region is very important. Having this kind of system could be beneficial to improve our design. So that's what I like to say. And this is field deployment. So there were challenges. So yeah, Prakash wanted to show this to you here. So we are using solar panel. So in snowy conditions, solar panel is covered by snow, and there were some issues and then also sensor damage, corrosion of the sensors, and also there's vandalism. So our one of the solar panel was stolen. So it's because it's public property. So there were challenges, but still we got the correct data. So in conclusion, so the proposed real-time wireless expansion joint monitoring system was successfully developed, I think. And then it was validated in 3 field highway bridges, and with smaller costs, although there were some challenges. So I think our product or this similar product can be helpful to improve bridge design for resilience of highway bridges. So I'd like to acknowledge the generous support from TIDC, and then U.S. Department of Education, and then UConn, and also in-kind contribution and support from technical champions from Connecticut DOT. So there are Bao, Andrew, and Sangyeo, and also timely responses from all 6 New England Department of Transportation. I really appreciate it. And last but not least, the valuable contribution from by student and Professor Song, Professor Han, and Professor Mala's students are gratefully appreciated. Okay, so a few photos, and thank you very much for your attention.